Recall Gauss's law for electrostatics. That is, the integral of E dot dA over a closed surface equals the enclosed charge over epsilon naught. This comes down to, if you remember, the idea that we have some sort of collection of charge. We pick some imaginary volume in it, and of course there's a field threading through our surface. We do that. And Gauss's law counts how many electric field lines enter or leave the surface, roughly. Roughly count of that. That's what the flux measures, how much electric field is entering or leaving the surface. And since field lines start or end on charges, it's proportional to the charge inside. But there's an equivalent for Gauss's law for magnetostatics, where we have some region and we have some magnetic field. But remember that magnetic field is always circular, right? Always has loops. And so when we do the integral for B dot dA, we're going to find that the flux exiting the surface is always zero. There's as much flux entering as leaving because there are no monopoles on which to start field lines or end field lines. And so the quote-unquote charge, there's no charge to magnetics, so the enclosed charge is zero. But there is no magnetic charge, so the amount that we have happens to be zero because there's none anywhere. This really just formally captures the experimental fact that there are apparently no magnetic monopoles. There are theoretical reasons why it'd be nice if there were monopoles, but we've seen no experimental evidence for it, and Maxwell's laws are obeyed particularly remarkably well in classical physics, so it kind of argues against it. It seems that there really are no monopoles. All right, Faraday's law of induction connects an electric field to a changing magnetic field. That is the integral of E around some path, right? So again, we say, let's take some path that we're going to pick. That's our with little step ds at any given point, and the change of flux through that piercing that surface we've just made tells the rate of change of that tells us how much electric field there is as we go around. So there's a magnetic equivalent to that as well called Maxwell's law of induction that connects a changing magnetic field to a changing electric field, and it looks very similar. The integral of B dot ds around some path is mu naught epsilon naught and times the rate of change of the electric flux that's enclosed in that path, that pierces the surface enclosed by that path. We can also, this bit is familiar. We've done integrals of B dot ds. We use them in Ampere's law to connect the magnetic field to the current, and we're going to come back to that in just a little bit. For instance, consider a charging capacitor. So a capacitor that has some charge, but we're putting more charge on it. There must be a current I that exists in the circuit branch with the capacitor, and it's delivering charge to the capacitor, which means the electric field is increasing. So we have a flux, and what the Maxwell law of induction tells us is that flux, which in this case they've decided to draw into the board, all right, bing, 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 into the board, that if we integrate around that, and we integrate in this sense because of the right-hand rule, if we integrate around this sense, we get a magnetic field that's being so there's like a circulating magnetic field around these changing electric field lines. So we combine this new result with the earlier one to get what's called the Ampere-Maxwell law, which is that the integral of B dot ds around some closed path is equal to two things, mu naught epsilon naught times the changing flux, plus mu naught times the current that's piercing through that surface. That is, you can generate magnetic field either by running a current or by changing electric flux, or by both. The magnetic field resulting from a change in electric flux looks exactly like that from a current. In fact, it's conventional to define something called the displacement current, although noted here, everybody who teaches this always says it's a terrible name because it puts some things in your head that aren't there. What is a displacement current? Like, it seems like a current that's been displaced, and it's not so clear what that is, although we'll see in a minute what motivated Maxwell to call it that. The displacement current then is just epsilon naught times d flux of E dt. As an illustration, before charging there is no magnetic field and there's no electric field. During charging we get magnetic field by the current looping around this way, and the current that's leaving looping around the same way. And then we get changing electric flux, right? We have field lines here, they're getting stronger, and so we get current that loops this way as well. During the charging, the right-hand rule works the same for both the real and this fictional displacement current. And then when we stop charging, there's some electric field here, but it's not changing anymore, so there's no displacement current, so there's no magnetic field induced that way. And there's no current here because there can't be current, or else this would be either charging or discharging. So there's no magnetic field there either. As an example, for a capacitor, parallel plate capacitor, the charge is CV, which is epsilon A over D, that's the capacitor, times the voltage, which is just E times D because it's the electric field is constant, so integral of E dot dl is just ED. So the charge on a capacitor is epsilon naught times the area times the electric field, which, by the way, has nothing to do with what we're doing today, and so it's a general result that might be useful to know. All right, but whatever. The current feeding it would have to be dq dt, right? If we're going to be increasing Q, we've got to bring in current to do that. And the current would have to be dq dt, which we see is epsilon naught A times dE dt. We could find the displacement current, which is epsilon naught times d phi E dt, but the flux through this surface is going to be electric field dotted into A. They're going to point in the same direction, so we're just going to get EDA, which becomes just EA, and A doesn't change. So we have that the displacement current is epsilon naught A dE dt. They're the same. Of course they're the same. It's as if the current continues through or is displaced across the capacitor, right? So the idea is we have, here's our capacitor, and we're bringing in current this way, and of course the current leaves that way, and it's as if it sort of goes across, as if there's a current flowing here, ID. And notice that even these does things like preserves the Kirchhoff junction rules, where current doesn't just stop anymore, it flows through, but it flows through as ID. This is why Maxwell called it displacement current, because it's as if the current gets displaced over or through the capacitor. It's still not a great name, but that's where it's coming from. It's probably important to point out that a lot of this stuff is modified, although not tremendously, in the presence of dielectrics. And so in a intermediate electromagnetics class, you'd also learn about things like the D field and the H field, which are sort of the connection between they're sort of the electric and magnetic fields in materials. We're not going to talk about that because it's not rewarded and because the class is about to end, but it's important to understand that it's a little bit more complicated when there are polarizable things around that you can, or for monopoles, well, I guess also for magnetics, you could have polarizable dipoles. And so it gets a little more complicated, but not too much. We traditionally put all of these results together as so-called Maxwell's equations, which are the pinnacle of classical physics. This was the high point that said, hey, what does it mean to do physics? Maxwell's the guy who did physics. He synthesized everything known about electrodynamics into essentially 4 equations. These are not the way that Maxwell wrote these equations. He didn't have vector calculus available. He didn't have the concept of vectors at all. And so it's way more complicated in Maxwell's notes, but properly translated into modern notation, it looks something like this. That we have Gauss's law for electricity, the integral of E dot dA is the enclosed charge over epsilon. Gauss's law for magnetism, that the integral of B dot dA is just 0 always. Faraday's law, that the line integral of E dot ds around some closed loop is minus the change in magnetic flux. And the Ampere-Maxwell law, which says the line integral of B around some closed interval is mu naught epsilon times the rate of change of the electric flux plus mu naught times I enclosed. You can kind of see a couple of places, which I guess I'll mark with maybe asterisks. If there were monopoles, you'd have a change here, because you'd probably have something like, and I don't know if this is true, but something like mu times the magnetic charge, whatever that is, over, instead of 1 over epsilon, you'd probably have mu naught times the magnetic charge. And then for this one, there would have to be some magnetic current, whatever that would be, some term, and I don't know, with some constants out here, I don't know what they would be, but something that would look like this, but the current here would be not dq dt, but dq magnetics dt. But they don't exist, so we don't worry about that. All right, and lastly, the forms we've been talking about are what are called integral forms because, well, they have integrals in them. And they're certainly true, and they're useful in certain contexts, but they're hard to apply in a general way because you've got an unknown unknown integrand locked inside some horrible volume or line integral. So it's more traditional to work in terms of what are called the differential forms, where instead of looking at, for instance, the charge enclosed in some region, we look at a given particular point. And we find things like the so-called divergence of E is the charge density over epsilon naught, and the divergence of B is 0. What these are saying, divergence measures, you've got a point, and they measure how much stuff is coming out of that point. All right, a high divergence would have would mean a lot of stuff coming out, and a low divergence means very little coming out. And so the magnetic one says there's no divergence, that at any given point there's no generation or loss of magnetic field lines. So yay. And then we have the curls here. These things, the curl of E is minus the rate of change of B. We've got to be careful because not only is this a three-dimensional vector derivative, but it's also a partial derivative, the explicit time derivative of B, how it depends on T. And we have the same thing for curl of B, which is something involving the current density plus the change in the electric field. And what curl measures is how much vorticity there is in the field. In other words, the field goes around, and maybe it goes around like this. And so there would be some curl to this kind of field. These come out of hydrodynamics, these interpretations, and Maxwell even made his arguments by analogy to water going past gears and rods and stuff to say this is what's going on. What we see here is that basically changing magnetic fields curl up or sort of twist up the electric fields, and changing electric fields curl up and twist up the magnetic fields. And that really brings us to the end of classical physics. After Maxwell comes a bunch of optics that are from Maxwell's equations, and then maybe 30 or so years later, we have the discovery of the electron and really the collapse of the classical model. And in that, Maxwell's equations end up having to be made relativistic and quantum mechanical, and it takes a lot of work, although they still mostly persevere.